Hello, I'm Vali Tawosi, a PhD student at Solar Research Group at University College London, and I'm going to present our work on investigating the effectiveness of clustering for story point estimation, co-authored by Dr. Afnan Al-Subaihin and my supervisor, Professor Federica Sarro. First, let's see how the developers and software engineers measure the amount of effort that is needed to develop a given task in software project. For example, this is a user story describing a task which asks the developer to create a multi-level navigation menu on the homepage of a travel application. A task description is called a user story in Agile development process. Well, in the Agile community, a popular measure for effort is a story point, but there is no set formula for defining the size of the story point. However, story point is a relative measure that represents an intuitive mixture of complexity and required effort to develop a task. The values are usually drawn from Fibonacci series or similar, like the one depicted in this picture. But note that the story points are unitless and only show the difference in the size of the tasks relative to each other. According to Usman and others, the most popular story point estimation method among Agile teams is through a meeting called planning poker. In this meeting, someone reads user stories and all team members contribute by voting for story point values and discussing their perspectives until all the members agree on the same value. Besides all the benefits of such meeting, this process can be time-consuming for the team, and human decisions can be biased and prone to error after all. It was almost a decade ago that researchers started investigating methods to automate this task. A completely random solution to this problem could be to randomly pick a task which is done in the past and assign its story point value to the new task at hand. A little bit wiser method that can reduce the estimation error would be assigning the task at hand the average story point of the issues completed in the past, which can be the mean value of story points or the median story point. Any intelligent solution should be able to outperform these simple baselines to be accepted as an effective estimation model. These are the two studies that we compared our results with. They both leveraged the textual information of task description to find similar tasks developed in the past and use them to inspire an estimation for the task at hand. Because, based on analogy, we expect similar tasks to take similar effort for development. The first approach, which is published in 2016, used SVM on a TF-IDF vectorized representation of user stories. We call this approach TF-IDF-SE. The second, called DeepSE, is published in 2019 at Transactions and Software Engineering Journal. DeepSE uses deep learning to create an end-to-end task description to story point estimation model. But we found that both these approaches sometimes struggle to outperform the median baseline. Interested readers are welcome to check out our other study where we investigate this issue. A preprint is available on our archive via the link provided in this slide. However, in the study that I'm presenting, we want to improve the status quo by investigating a text clustering-based approach. Our approach is called LDA-based hierarchical clustering for story point estimation, or LHC-SE for short. The proposed method relies on clustering similarly described tasks such that, given a new user story, its story point can be derived from the story point values of the issues deemed most similar to it. Basically, the issues that reside in the same cluster. I'll get into it shortly, but first, let's see based on specifically what do we cluster the issues. We use latent directly allocation, or LDA for short, which generates a set of topics derived from the document's word distributions. Then, using the LDA model, each document, or user story, can be represented via a vector of fixed length filled with the degree of relevance of the user story to each of the topics. So once we have a numerical representation of user story, we can use common similarity measures like cosine similarity to quantify the degree of similarity between each pairs of user stories. Then we use hierarchical clustering to agglomerate similar user stories bottom up until we have one big cluster. Once we had the dendrogram, we can cut it at any level, let's say K, and get the clusters at that level instantly. This brings us to an important question. How do we choose the best K? 3 strategies used to choose the best K. We use a validation set and choose the K with which, in 2 strategies, the estimation models of the resulting clustering produce the lowest mean absolute error and the lowest median absolute error when used for a story point estimation. As the third strategy, we consider the K with which the resulting clusters have the highest silhouette index. The silhouette index is an internal measure of cluster quality. Once the clusters are formed, a story point estimation model is built using issues in each cluster. We investigate 3 models, 2 of which are the mean and median baseline estimators, and the third closest point-based estimator, which returns the story point value of the closest issue to the queried issue as the estimation value. When we want to use this model to estimate a story point for a new user story, we find the closest cluster to the user story and use the model trained on that cluster to estimate the story point. We investigated 3 research questions. By the first research question, we want to see if LHC-SE can effectively estimate a story point for new user stories. In the second research question, we look into how inclusion of additional features help improve estimation accuracy of our proposed model. And in our final research question, we compare our model to the existing approaches, namely TF-IDF-SE and DEEP-SE. We measure the performance of the estimators based on the mean and median absolute errors of their estimation and win-loss tie scores, for which we perform a Wilcoxon rank sum test at 5% significance level and consult the resulting p-value to determine if a model wins against the other. As for data, we use a large number of issues extracted from the Tawosi dataset. We recently made this dataset publicly available, which comprises over 500,000 issues from 44 projects mined from 13 different open-source Jira repositories. A full description of the Tawosi dataset can be found in a paper recently accepted to MSR 2022. Preprint is available on our group's website. In the clustering study, we used a subset of this dataset with more than 30,000 issues extracted from 26 projects. To answer our first research question, we compared the 9 models produced by the combination of 3 case selection strategies and 3 estimation strategies to find the best performing strategy over all projects. The results of win-loss tie showed that the variant with MAE-based case selection strategy with cluster median estimation model is the best performing one. Then we compared this variant to the 3 baselines. The results showed that LHC-SE easily outperformed random guessing and mean baselines and performs similarly to the median baseline. To answer the second research question, we created 2 additional models by first adding issue type and component and issue description length to the feature set and called it LHC-SE, and second, adding TF-IDF vector representation to LHC-SE, which then is called LHC-TC plus TF-IDF-SE. The results showed that 3 models perform very similarly. However, LHC-SE wins in 1 more project and loses in 1 less project against our basic variant. LHC-TC plus TF-IDF-SE, on the other hand, performed slightly better than the basic variant by losing in only 1 less project, but is still not better than LHC-SE. So we choose LHC-SE to compare to the state of the art. To answer our final research question, we compared LHC-SE to DEEP-SE, TF-IDF-SE, and the 3 baselines. As we can see, at least 3 of the models perform very similar to each other, but our clustering approach performed better than all the other methods, while its score is only slightly better than median baseline estimator. Our findings show that LDA is able to capture information latent in the issue description and enable the clustering algorithm to form useful clusters for story point estimation. Augmenting LDA-generated posterior topic probabilities with extra features from issue reports help the clustering algorithm to form a better clustering solution. But considering the level of complexity of the model, time and resources consumed to build it, and the interpretability of the model. The median estimator can be viewed as the more favorable model so far that can be used in practice. Based on our findings, we also provided some implications and suggestions for future work. We note that the fact that a naive estimation approach, such as the median one, provides comparable and in some cases even better results than much more sophisticated techniques like deep learning and LDA, indicates that we still need to work on better solutions to achieve a higher accuracy. This also suggests that future research on story point estimation might need to pay more attention to the data rather than the estimation technique when building prediction models. In fact, issue reports, especially in open source projects, are not usually written in a structured or formal way. Therefore, they can be very noisy, and it's possible that by using tailored text preprocessing and data cleaning, the accuracy of the proposed model can be improved. On the other hand, improving the quality of the user stories written by the authors of the issue reports could yield less noisy data for model building, therefore improving the estimation accuracy. As a summary to this presentation, we talked about the story points, how they are used in agile software development process. Then we saw how an LDA-based clustering method can be employed to estimate the story point for issues. And we compared our approach to 3 baselines and 2 previous work, including the state-of-the-art deep learning-based technique. And finally, we shared our findings and laid out some suggestions for future work. Thank you so much for listening. I'm up for any questions.